This presentation is on 3.2 Paths and Circuits as a part of the whole graphs section for Math 5 CST. In this PowerPoint, we're going to go over simple paths, simple circuits, an Euler path, an Euler circuit, Hamiltonian path, and Hamiltonian circuit. The difference between paths versus circuits is what we're going to go over with first. So in a graph, a path is established when you can travel from one vertex to another by following the edges. The length of a path corresponds to the number of times you travel from one vertex to another. So basically, how many vertices do you pass through when you go from one to another? That's the length. The distance between two vertices A and B, written DAB, so D for distance, corresponds to the length of the shortest path that connects the two vertices. So I'm going to show you an example. So here is a graph. And in this graph, please note the following. So remember that paths are just from going from one vertex to another. So D, E, F, and E, F, G, H, and D are both examples of paths, although there are several in this graph. The length of path DGFE is 3 because here we start at D, then we go to G, that's 1, 2, 3. So we're passing through 3 vertices basically. And the length of path, here's G, so we're starting at G, then D is 1, back D is 2, back to D is 3, G is 4, and H is 5. So if you count how many vertices you pass after the first one, that's the length of the path. The distance between F and H is 1, and the reason why it's 1 is because that's the length of the shortest path from F to H. Okay, because there's several different paths that we can get to by going from F to H, but the shortest one is just length of 1. And the distance of HE here, the shortest path is 2 because you can go HDE. But keep in mind that, yeah, of course, you can go HGFE, but that's not the shortest path. The shortest path has a distance of 2. So we say that the distance of HE is 2. Next, we have circuits. A circuit is a path, except it starts and ends at the same vertex. Whereas a path goes from one end to another end, a circuit makes a circle, so it starts and ends at that same vertex. Paths don't need to end at the same vertex that it started at, so that's the difference between circuits and paths. In the adjacent graph, I have A, B, E, B, and then back to A is one circuit because we're starting and ending at the same vertex. And another example would be going from D, C, E, B, then back to E, and then finishing going from A to D because we're starting and ending at D. It's a circuit. Paths and circuits are simple if they contain no repeated edges. So yeah, of course you go like A, B, A, D, A, B several times. But a simple path is when you don't repeat edges, or a simple circuit is when you don't repeat edges. So let's talk about simple paths. In this case, we have A, B, C, and D. No repeated edges, that's an example of a simple path, and we're starting and ending at a different vertex. We also have an example of F, E, C, B, A, D, and then back to C is another example of a simple path because first we're starting and ending at a different vertex and we are not repeating edges. If we look at some simple circuits, one example would be going from A, B, C, D, and then A. We're starting and ending at the same vertex and we're not repeating any edges. We're going to talk about Euler paths and Euler circuits. I know you think that it's pronounced Euler, but it is pronounced Euler. An Euler path is a path that visits every edge in a connected graph one time. An Euler circuit is the same thing as an Euler path, except it starts and ends at the same vertex, but it visits every edge in the graph one time. This is how you can tell if a graph contains an Euler path. 1. It contains an Euler path if all vertices are of an even degree, and by even I mean like 2, 4, 6, 8. This path starts at any vertex and ends at the same vertex, called an Euler circuit. So this path will be an Euler circuit, not so much an Euler path. Or if there are exactly 2 vertices of an odd degree, and by odd I mean like 1, 3, 5, 7, 9. This path starts at a vertex of an odd degree and usually ends at another of an odd degree. So this is how you know. And we'll take a look at some examples. First, the Euler path. Remember, it visits every edge just once, and because it's a path, we're going to start and end at a different vertex. My example is E, B, C, D, E, A, and D. So I visited every edge once, and I started and ended at a different vertex. Okay? Notice that there are two vertices with an odd degree. So here E has a degree of 3, and D has a degree of 3. And because we have 2 with an odd number, that's how we know that there's an Euler path. Also keep in mind that just because I gave you this example of an Euler path, there are several different kinds. Think of this as a game. It's very much a maze kind of game where you need to figure out the shortest path or the path that best fits. So because I gave you this, it doesn't mean that this is just the only answer. There are several different ways that you can start your Euler path. Let's look at an Euler circuit. And remember, it's the same thing as an Euler path where it visits every edge once, except it starts and ends at the exact same vertex. So my example is A, B, E, D, C, E, and A. I visited every single path in my, I visited every edge in my circuit, in my graph, and I started and ended at A. And again, just because this is my example doesn't mean it's the only example. Note also that all the vertices here have an even degree. A has 2, B has degree 2, E has degree 4, C2, and D2. And remember that I said that if all vertices have an even degree, it tells you if it has an Euler path, and in this case, sits specifically in Euler circuit. Let's move away from Euler, and we're going to talk about Hamiltonian paths and circuits. A Hamiltonian path is a simple path, so no repeated edges, that visits every vertex, not so much every edges, but every vertex of a connected graph only once. And as you can guess, a Hamiltonian circuit is the same thing, except it visits every vertex of a connected graph only once, starting and ending at the same vertex. Let's start with a Hamiltonian path. So here's a graph, and here an example of a Hamiltonian path, meaning it visits every vertex once. I'm going to start at D, go to E, C, A, and then B. Now I didn't visit every edge, but I did visit every vertex once. Can you find an Euler path in this just by looking at it? And remember, an Euler path is visiting every edge of the graph at least once, starting and ending at a different vertex. My example is going D, E, A, C, E, B, and then A. Again, you can find several other ones. Let's look at a Hamiltonian circuit, and here's your new graph. I'm giving you the example of a Hamiltonian circuit. Remember, visits every vertex, but a circuit starts and ends at the same vertex. I'm going to start here. A, E, B, C, D, A. Didn't visit every edge, but I visited every vertex. And in this case, can you find an Euler path? My example starts with B, E, A, D, B, C, D, E, and then all the way around here to C. So I visited every edge of my graph at least once, or just once. So just to recap, paths are when you can walk around the edges of a graph from one vertex to another, starting at one and ending at a different one, whereas circuits are when you walk around the edges of a graph, but you end at the same vertex that you started with. We call paths and circuits simple if they have no repeating edges. Next, we looked at Euler paths and Euler circuits, which is when you visit every edge of your graph one time, and circuits are the same thing, except it starts and ends at the same vertex. That's an Euler circuit, visiting every edge of the graph one time. Then we looked at Hamiltonian paths and Hamiltonian circuits. And in this case, we visit every vertex in the graph just once. For a path, we start and end at a different vertex. In a Hamiltonian circuit, we start and end at the same vertex, visiting every vertex of the graph. That is the end of 3.2, paths and circuits. Next PowerPoint, we are going to be introduced to weighted and directed graphs.